All right, it's time. Let's get started. So, so far in the last few lectures, we have discussed supervised learning, and we said that there are at least two types, right? Depending on the label ym. If the label is discrete, then you are trying to make it discrete. You're trying to make discrete decisions. So it's classification, separate the data into different classes. But if the label is continuous, we have another name for it, regression. Yeah. So that will be today's main topic. And in particular, we will focus on the linear form of regression. So we have linear regression. And we're going to set it up. Of course, we have the training data set, or the training set, D. Just as before, yeah, we have these data points, except that in these data points, the ym is continuous instead of discrete, that's all, right? Yeah, so xn is a vector in d-dimensional space. Ym is just a real number, yeah? And then we have to have a decision rule. And as we said before, this is also called the hypothesis set. The allowable hypotheses that you can choose from. And it's also called the learning model very often. Okay. In the sense that you have a linear model, you have a quadratic model, ninth order polynomial model, and so on. Yeah? Okay. The decision rule is expressed in terms of a y hat, the estimated label, right, is a function of the input x, yeah, just as before. And now we have a linear combination of the features in x, x1 plus da 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 plus wd, xd, right? It's a d-dimensional input. So this is different from our previous one, the binary classification. When in binary classification, we take this weighted sum and then we send it to a sign function to check whether it's positive or negative. Yeah, but here we don't do anything because our output itself is just a continuous number, right? So we just simply take the weighted sum of the input values. So just as in classification, we also define an augmented form because that turns out to be a bit more convenient to use. Which is, we change w vector to w0, w1, da, 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 to wd now, yeah? And then we have a new x vector that includes a x0, which is always equal to 1, right? x1, da, da, wd, yeah? So far it's the same as what we have seen before, right? And once you have this augmented form, then the y hat will be of hx is this weighted sum can be written as the inner product between w and x, again, just as before, yeah? So just the beginning point of the perceptron, but we don't do the thresholding for positive or negative. Yes. Oh, yeah, yeah, thank you, of course, thank you. And then what is the criterion for our optimization? Yeah. Again, of course, the training error that we want to minimize. Yes? Nothing else is different, yeah? This is just still the same weighted sum, yeah. We're just learning about this y, this weighted sum. Yeah. So we don't care whether it's a positive or negative. We just know the exact number. Yeah. So the criterion E in, the training error, we can define it as the average square error. Okay. So average over the sample that we have. So n, small n goes 1 to n. Yeah. The square error will be the error, of course, of the true label, which is yn, and our estimated label, our y hat, right? So it's going to be yn minus y hat, which is simply this inner product, right? And we're going to square that because this one can be positive, negative. Yeah, we take a square so that it's always non-negative. And this whole thing, this square error, is also denoted by en of w, like that, for the nth sample. Yeah, so this is the squared error on the nth example. Yeah. Then altogether, E in will simply be the average square error, right? Yeah. So far so good, right? Everything is nice and simple. Yeah. So we just want to get an estimation that's as close to the true label as possible. Our true label is yn. That's why we take the difference between them. Yeah. We take the square error between those two. And our goal again is to use our data, given now some kind of historical data, right, in practice. That's what we have. And then we find this W. Now it's in d+1 dimensional space because it's augmented, in order to minimize E in, the training error. Yeah. Again, for now, we don't care about E out, right? We don't care about the testing error yet. Yeah. Yeah. Let's take a look at a quick example. Suppose you have a in a one-dimensional problem, just x one-dimensional. So don't even have to write the bar at the bottom, right? Suppose this is your advertising money. Advertising dollars in 1 week. Yeah. So of course now d equals to 1, right? In this case, yeah, in this example. And suppose that you have the output, which is the amount of sales that you generate in 1 week. So this is for a company, right? Yeah. So you put in some money for advertising, and then you observe how much money you make or how much sales you make in that week. Yeah, and that's why it's your sales, that's your output. And advertising money is the input. And of course, you can collect information over time, so you have some historical data. We call it D. Yeah, the same as what we have denoted so far, like that. Yeah, you have n data points that you have collected, and your question is, well, how can I learn? What can we learn from these data points, right? Well, what we want to learn is the mapping between advertising dollars and the amount of sales that you make, right? That's what we want to learn. Yeah. Given this, you want to learn this mapping, this unknown function, right? Before this, we don't know yet, how much money I should put in order to generate that amount of sales. Yeah. You want to learn about it. So therefore, you're trying to learn the function that maps between x and y. So pictorially, you have an x and y like that. Again, x is a one-dimensional thing, right? Maybe in different weeks, you're collecting data that looks like this, right? In some weeks, you do better. Some weeks, you do worse. Who knows, right? Yeah? You have data like that. X-axis is the input, the advertising dollars, and y-axis is the your amount of sales. Yeah? Yes? That's a good point. I just wrote this in terms of our previous notation. But in general, it's a vector. But in this example, it is not. Very good point. Thank you very much. So we don't write vector here. There's no need because it's a one-dimensional space. Yeah. So these are the data points you have. Yeah. And you want to predict that function, and you say, well, I want to use a linear model to predict it, right? So basically, we want to fit a linear model through these data points, right? So the model with y equals w0 plus w1, x1, yeah? And this is the kind of thing that you have done even in high school, right? So, you know, the idea is very simple. You just try to find the best line that goes like that, yeah? And this line is supposed to minimize the square error. Yes? This problem is just a linear regression problem. That's the name. Okay. So in a one-dimensional example, we get into something that you have seen before, pretty much, yeah, in high school. Yeah. Now, in reality, of course, things can be a bit more complicated. So maybe your advertising dollars is not just one single pot. Maybe you want to split it into advertising on TV, advertising on radio, advertising on internet. And you want to know which one gives you better benefit and what should be the perfect combination for you. Yeah? Now you have to learn that. Now you have a high-dimensional linear regression problem. So let's say we can have a refined model which says that now x is a vector of 3 items, 3 numbers. Let's say it's the ad dollars on TV, yeah, ad dollars on radio, and ad dollars on the internet. Again, you can collect the data points over time, yeah, and then now you have to do a d equals to 3 regression problem. Well, let's put a y hat here, yeah. Y hat is going to be equal to w0 plus 1 x3 like that, right? And these weights, the w's, just indicates how much emphasis you should put on that particular value of advertisement, right? Because a larger wi would give you will indicate an xi that is more profitable, right? Yeah, but you just have to learn about that. You have to use your historical data to learn which one may be more profitable, for example. Yeah, what is the right combination? So to discuss how we should solve this problem, a problem like this, well, we have to go into a bit more mathematics, a bit more algebra, okay? In particular, we have to use your linear algebra skills, yeah? We're going to use a matrix vector algebra representation of this problem, because that turns out when you write things into matrices and vectors, you get a very clean form. Algebraic representation. Okay. So first of all, we have the data points. We're going to put those data points into a big matrix called a data matrix. The capital X, that's how I write the capital X. Okay. The data points are x1, x2 to xn, right? So each data points I'm going to put into a row of this matrix. So therefore I have to make a transpose. Yeah? By convention, our vectors are column vectors. Okay? So when you want to put in the matrix as a row, you have to take the transpose of the vector. Okay? T here represents transpose, of course. And then we're going to have x2 transpose, all the way to xn transpose. Okay? So now clearly this is what is the dimension of this matrix? There are how many rows? N rows, right? So n, each row has d plus 1 elements, yeah? Because that's the length of your data point. Okay, so n by d plus 1 matrix, pretty big usually, yeah. And then we also have the target vector, which is our output. Let's call it y, like that. Basically, in our previous example, would be the amount of cells per week, right? So y1, y2, to yn. Yeah, and clearly this is just a n-dimensional column vector. Yes.
Why is it d plus 1 and not d?
Oh, because this is a augmented vector. Yeah. And of course, we also have the wave vector, W, that you already know it is a d plus 1 column vector. Yeah? And after this definition of variables, we can rewrite our linear regression model in the vector form as well. Yeah? Y hat is this vector, of course, will be just collection of y hat 1 or y2 hat and yn hat. Yeah? These are the predicted values. And we know that by our definition, these are the inner product or dot products between the weight and the corresponding data features. Just like that, right? Okay. So far so good, right? This is all just by definition, right? By definition, our y hat is equal to the inner product between w and x. Yeah? Now, inner product, remember it is a symmetrical operation, right? I can flip the order of those two, okay? Let's flip them so that I can take this w out onto the right-hand side as a column vector. Okay, if I flip the order of this inner product, then I'm going to have x1 transpose, x2 transpose, xn transpose, multiplying the vector w. Yeah, okay. All of this is basic algebra, right, that you have learned about in either year 1 or year 2, right? Now, why do I want to do this? If you compare this one, the last part, with our definition of big X, you see that that matrix there is just simple big X, right? So therefore, I can rewrite this y hat as just big X times W. Very convenient, very nice, very clean form, right? Okay. So this is our linear hypothesis, our linear model. With that, then we can write our error, the training error, E in, as a 1n. If you recall the definition of E in, where do we have it? Yeah, here we go. On top there. Is this average square error, yeah, per sample error. But this sum of the squares of elements, right, can be viewed as the norm to 2 norm square of the difference of vectors. Okay? So I'm going to rewrite that as the 2 norm square of the yn vector minus the y hat vector. Okay? So this is going to be y vector minus y hat vector 2 norm square. Yeah? And we want to minimize this E in, okay? Or in the perfect world, in the perfect case, E in could be 0, right? Then everything is correct. You may always make correct predictions. Yeah? Let's take a look at this case. When is this E in equal to 0? In other words, if you want this E in to be equal to 0, what do we really mean? Yeah, y has to be equal to y hat. Exactly what? Well, the entire vector has to be equal. So every single element have to be matching, have to be exactly the same. So y is equal to y hat. But when does this happen? Well, let's take a look. Yeah. We know that the true label, we want to find a w that can give you this, right? Because y hat is the inner product, right? Yeah. So we want the ym to be equal to the y hat, and we need this to be true for all m values, because these vectors are equal. So every single element in those vectors have to be equal, right? Yeah. Every single element has to be equal, every m value. So this is a linear equation, right? Yeah. We already have xn, we also have yn. These are historical data, right? Xn, yn are historical data. We already have. What we don't have is w. We want to find w. To find w, we're basically solving equations, right? How many equations do we have, and how many unknowns do we have? We have n linear equations, right? Number of linear equations is n. How about number of unknowns or variables? Think again. What are the unknowns? It's the w's. How many w's values do we have to decide? What is that dimension w? D plus 1, yeah? There are only d plus 1 values that we have to decide. Yeah, so this is d plus 1. So we have n linear equations, and we need to solve for d plus 1 variables. Under what conditions can we solve this problem? You know, right? Okay. You have n has to be exactly equal to d plus 1. Then you have hope that you can have a unit solution. Unfortunately, in practice, you always want to have big data, right? N is huge. Usually n is much larger than d. Okay? So therefore, you cannot find the exact solution to this problem. This is an overdetermined set of linear equations. Okay? So in practice, n is much greater than d plus 1, or just d is good enough. Yeah. So we don't have an exact solution. To this set of linear equations. It's overdetermined. Yes? Yeah, in some cases, when you don't have a lot of data points, n will be smaller. In that case, what happens when you solve this in linear equations? No. This is going to be an underdetermined system. So you have more degrees of freedom than you have number of equations. So you have infinitely many solutions. Now, so in general, we cannot find the exact solution. We cannot solve this and hope to get 0 for E in. Yeah? That means E in will always be positive. Yeah? So our only hope is to minimize it, to make it as small as possible. Usually it does not go to 0, because usually we have n greater than d. Yeah? Okay? So instead, we try to minimize okay? And the method we will use is called the least squares method, or the least squares solution to this minimization problem. Least squares solution. Just basically we have a bunch of squares, right? The sum of squares, and we want to minimize that. Least squares. So again, we want to minimize over W this E in of W, which is by definition these two norms squared, right? Oh, sorry. Okay. to solve this minimization problem, we try to take the derivative, right? Because this is a nice quadratic equation. So let's define first the function that we want to take the derivative over. So it's let's define f of w, just the e in the w, except without the factor. Yeah, we don't have to worry about the 1 over m factor anyways. Yeah, so let's just make things a bit cleaner and get rid of the factor. Yeah. So we want to minimize this f of w. Yeah, this is our loss function that we want to minimize. And the common thing that we have learned how to do, either in high school or in maybe first year calculus, we take the gradient, right? So, but before we do that, let's write down a few more details about this fw. And this is y hat. Remember, y hat is simply x times w, like this, right? You can do that, yeah. And just as an aside, this is also equal to, we are not going to use this one. The sum of squares, right? xn minus yn squared. Where this one is our small en, right? Yeah. This way is just a cleaner way to write the same thing, right? Cleaner way to write the sum of squares. So let's take the derivative of this guy. But this one, fw, is a multi-input, multi-variable function. Yeah. So what do you mean by the derivative of this? Well, we can only take partial derivatives with respect to all of these different variables, w0, w1, and so on. Right? Turns out we have a fancier name for that derivative. We call it the gradient of this function. Yeah. So many of you probably have already heard of this. But if you're not, that's okay. We're going to define it right now. The gradient of this function is denoted by nabla of f, like this. Just a collection of the partial derivatives. Partial f, partial w0, partial f, partial w1. Again, notice that we almost always use column vectors instead of row vectors. Just a collection of all of the partial derivatives. Put them into one vector. Now you have the gradient of the function. Okay. Now, of course, this corresponds to the derivative that you have seen before when d is equal to 1, right? So if you look at the d equal to 1 case, yeah, fw, yeah, maybe a function that looks like this, yeah, and say, well, I want to know the derivative of this point. You could look at this point and just draw the asymptote, right? Not the asymptote, the tangent line, yeah. So this would be f prime of w. Right? F prime of w would be just a one-dimensional version of the gradient, right? Yeah, because the gradient is nothing more than the derivatives. So in particular, it points, the gradient points in the direction of the steepest increase of the function. It points in direction of steepest increase or increment, if you want. Yeah? Ascent, sometimes also that's the word. Steepest ascent. Yeah. And in general, it is a vector in space, right? So it's just pointing in a direction that that the steepest climb up of the mountain. Okay. We're going to use the gradient quite a lot throughout the course. Now, how do we calculate the gradient for our particular function? Our function looks like this, right? This f of w, it is a 2 norm square. Yes? Oh, it's WD because we start from W0. Right? From 0 to D, there are D plus 1 terms. Okay. Yeah. Small what? Oh, that's just the error per sample point. That's the error for the nth sample point. Yes, that's right. Yeah. So the first claim is that when you take this derivative, you take the gradient, what are you going to get? Before we write this, let's look at an example of one-dimensional case. If our FW, one-dimensional, right? Here, this is just x times W minus y, xW minus y squared, right? How do we take a derivative? F prime of W will be chain rule of differentiation, right? First take the respect to the square, so you have 2 xW minus y, and then you take a derivative of the inside, yeah, which gives you x, right? That's the derivative. It turns out that when you do the gradient, it follows the same form. Remember our FW, again, has this square form, right? So it turns out that you just you get 2 times x transpose, and then multiplying whatever that's inside, minus y like that. Okay. The only difference is that you have to worry about this transpose here a bit. Yeah? These are the formulas that you should have already seen in your linear algebra course. Okay. But I know, it's been a while. If you have not used it a lot in other courses, then you would need some time to get used to it again. Yeah. And for this week, the reading assignment, part of it will be the textbook's Appendix B, which is a review on linear algebra. Okay. So make sure, if you're not comfortable with linear algebra, make sure you read that carefully, pick up the required knowledge. So number 2 is the claim is that, well, we want to minimize this function, and I know the gradient of the slope. Right? I already know the derivative. How do I minimize the function if I already know the derivative? Yeah, set to 0. Yeah, in particular, this one is a convex function like that. Yeah, you have to prove it, but it's clear from the picture, anyways. Yeah. So if you set the derivative to be 0, then you get to the bottom point. Yeah, the minimum point. Same for high dimensional space as well. So it turns out that the least squares solution, which is the solution that minimizes the function FW, is one where the gradient is equal to 0. Least square solution. Let's call it W of LS. Is in the form such that f the gradient WLS is equal to 0. Yeah. And of course, the corresponding example in the one-dimensional case, of course, it says that the f prime W is equal to 0. Yeah. Yeah. Now just notice that here is the gradient equal to 0, so this is going to be a vector of zeros. Yeah? So every single partial derivative will have to be equal to 0. That's what it means. Yeah? Every single partial derivative in the vector of gradients has to be equal to 0. So knowing this, then how do we solve the problem? Well, we know that means that our 2x transpose xw minus y, which is what we seen, yeah, as the gradient on top, right, first line there, has to be equal to 0. Right? How do you solve this for w? Yeah, just do your simple algebra, right? You can break up this difference into 2 terms, shift things around, and you're going to get x transpose times xw. Oh, there's a bar here, sorry, is equal to X transpose times Y. Yeah. Now, those of you who are comfortable with your linear algebra, think, oh, okay, yeah, in that case, then I just take the inverse of this guy, move it to the right hand side, right? There's a small caveat there. You have to make sure that this product here is invertible, okay? And we have to make an assumption that it is invertible. Yeah? But we can make the assumption in a bit more intuitive way, okay? Let's see. The assumption is that the columns of X, remember this X? Usually it's a long matrix like this, right? This is m by d plus 1 matrix, right? Our X. Yeah? You remember each one of these rows is one of the sample points, right? That's our big X. Okay. What we want, in order to guarantee that that product is invertible, we need the columns to be linearly independent. Yeah? We want this matrix to have a rank of d plus 1. So the d plus 1 columns of X are linearly independent. Okay, that's what we need. Now, a matrix, the rank in terms of columns and rank in terms of rows will be the same. So this is of the same as saying that we need to have d plus 1 examples that are linearly independent. So we have d plus 1 rows that are linearly independent. Yeah? So it's the same as saying that there exists d plus 1 rows. Basically, they are data examples. Of X that are linearly independent. Okay, you just need d plus 1 of them. Okay, the rest, whatever they are, we don't care. Okay. So in general, so this condition is actually quite easy to satisfy, right? If you have many example points, then usually it's easy to find d plus 1 of them that are linearly independent. Okay? Therefore, in general, this matrix will be of rank d plus 1. Okay? Is it convincing? Yeah? Okay. I see that I think we're less comfortable than maybe the last lecture, right? Because these things you're not, maybe linear algebra is not such a hot topic for you guys, yeah? Okay. But again, read that appendix of the textbook and also maybe find some tutorials on linear algebra as well if you don't quite remember what you have learned before. Okay? So what we're saying then is that the rank of this matrix is d plus 1. Right? Okay. And therefore this X transpose times X is invertible. Can someone tell me the size of this X transpose times X? What is the size of X transpose X? Yeah, because X itself is d by d plus 1, right? X transpose, then it is d plus 1 by m. So when you multiply these two together, the m part goes away. You have d plus 1 times d plus 1. Yeah? Okay. Again, if you're not very comfortable with this, just take a little bit practice, a bit more reading, yeah? A bit more familiarity. You feel comfortable very soon. But yeah, myself also not an expert on linear algebra. So I mean, I always have to think about these matrices, how do I rotate them, what is the dimension and so on. It takes a bit thinking, yeah? Don't worry, it could get a bit confusing at the beginning, okay? So this one is a d plus 1 by d plus 1 matrix, and it has d plus 1 rank. So it's a full rank matrix, therefore it is invertible. You can safely invert it and with no problem. Yeah. So therefore, now we know that the WLS in this case will be simply moving this inversion of the matrix to the right hand side, right, and then keeping whatever that's on the right hand side, right. We're just solving this original problem there. Yeah. The top there. We want to solve this. We just move the X transpose X to the right hand side. Yeah. After inversion. So and that's that. That's our least square solution. Okay. Oops, what happened? Oh, did I delete it? My goodness. Undo. How do I undo? No. Undo. Here we go. Yeah, good. All right. By the way, in the textbook, the notation is W of LIM, like that. LIM, of course, stands for linear regression, right? But LS is actually more common in the other parts, other books. And also later today we're going to talk about regression version, regularized version of LS. In that case, we use RLS. So I prefer to use LS instead of the textbook's LIN. Okay. This one is actually a very famous form. Yeah, although you probably don't have to remember it. It's so important that we have a name for this. The term that's before Y. It is called the pseudo-inverse of the matrix X. Okay? You should have heard of pseudo-inverse in your linear algebra course, but let's review it anyways. The pseudo-inverse X dagger is simply defined as this transpose. It's not dagger, X minus 1 X transpose, like that. Yeah? It's called the pseudo-inverse of X. Okay? Why is it called the pseudo-inverse? Let's see. A few notes. First of all, what happens when I multiply this X dagger by X on the right-hand side, like that? What do we get? So let's write it out, right? X transpose, X inverse, X transpose. Now I multiply another X. Yeah. I can use the associative rule. Yeah, I can associate these two together, put them together. Okay. Now you see that this one is simply inverse of that, right? These two multiplied together, of course, just what is the name of the matrix? Identity matrix, right? So just kind of like 1 in our scalar algebra, right? So of course, kind of the inverse then, right? So this pseudo-inverse, kind of like the inverse of X, yeah, has this property. When you multiply them together, you get an identity matrix. But matrix multiplication, you have to be careful though, right? Matrix multiplication, there are two directions, right? When you put X on the left-hand side, the answer may not be the same as the one above, right? It's not a symmetrical operation. So this one, what do we get? Let's put this together. X transpose X, inverse, X transpose. Like that, right? Can we simplify this further? Turns out no. In general, this is not equal to identity. Okay, that's why it's a pseudo-inverse. Okay, not the inverse. Okay, in fact, X is not invertible. We know, right? X is not even a square matrix, so it's not invertible. We can, at best, have a pseudo-inverse. Okay. Number 2. Why do we have a pseudo-inverse as a solution for these squares? Yeah? Let's see. So our problem was originally we want to solve this, right? X, W. We want to solve this problem, search for W. Yeah. In the one-dimensional case, we have y is equal to xw, like that. And then we can say, well, to solve for W, then it's simply x is maybe W equal to 1 over x times y, right? Provided that x is not 0. Okay. So therefore, in the in general, we want this multiplying something, multiplying y, right? Just by our simple algebra rules. Yeah, that's what we want. We want to look for something to multiply y to get the w, right? Inspired by the one-dimensional case. Yeah, and we know the one-dimensional case, we get a inverse of x. But in general, our x is not invertible. Yeah, but the idea is to get something that looks like an inverse, right? Yeah, so it turns out that mathematically we have shown that you just put in a pseudo-inverse instead of any kind of inverse. Yeah, so it turns out that the least square solution gives you x pseudo-inverse times the vector y. Okay, and actually intuitively makes sense. Yeah, this one I just want to say, just as before we said, there's no exact solution, right? Because it is a over-determined system in general, because we have big data. Last thing I want to mention here is that if given you have the least square solution for W, then in testing, what is it? Let me just say, let me write this, testing, yeah? Testing, if you can do, maybe not, no, doesn't have to be testing. In general, let's just say, yeah, I should not write more than that. In general, then what we're saying is that our estimated label is equal to this, right? X times our least square solution. So x times the least square solution is this pseudo inverse times y. Yeah. So we can think that there is a matrix like this that serves as a transformer to map from the true labels to the predicted labels. Yeah? So there's a projection of this vector, the true labels, to the vector of predicted labels. And that projector, the projection is x times the pseudo inverse of x. So this is a projection matrix. And when we talk about projection, then you think, well, that reminds you of geometry. Yeah, projection of a point onto something. And in fact, there is a geometric interpretation of the least square solution. And we're going to take a look at that in 10 minutes after we take a break. Yeah?
By like, there's no exact solution. You mean like there's no single solution? Because like if there are many lines and then
No exact means that you cannot make it exactly equal. Right? We cannot solve this because it's an overdetermined system. There's no.
It's like you have more equations.
That's right. Yeah. Yeah. So you never solve this equation.
So does that mean like there are like multiple points that they are intersecting? Or is that what like overdefined mean? Like if you have like because if you have a line that's like into the plane, if you have a line that's number of variables too, and then
No. We're looking for a single line. All of these equations, we don't have a single line to fit all these points. We have more points than degree of freedom to fit those points. So our line will not be an exact fit. So in the one-dimensional example, it will be here, right? There's no way to find a single line to fit all of these points.
Oh, okay.
Yeah? That's not an exact solution, right? No matter what you do. Oh, you cannot do that in matrices. Those canceling rules only works when you have scalars. They don't work when you have matrices.
And one more question. So, while we assuming that while taking the minimum, isn't our goal that we take the steepest part? So, for steepest part, we need the second derivative to be zero.
No. We want the first derivative to be 0. We don't want the steepest part. We want the part where it's right at the bottom, so that
Minimum.
you cannot move any lower anymore. When you cannot move any lower anymore, that's not the steepest part, right? That's the flattest part, actually.
Okay, yeah.
Yeah.
But why do we? Okay, so what's the need of knowing that which is the steepest increase? Like, why do we have to know that?
Oh, because if the steepest increase is 0, then that means that you are at the flat part. Right? If the steepest direction, you can go in any direction. No direction, you can move any higher. Then you are
So
at
that's
the.
where the loss function is at minimum.
That's right. Yeah.
Okay. And one more question. So, why is that this data matrix it's not invertible in real life?
Well, because it is not a square matrix. Only square matrices are invertible. You cannot invert a non-square matrix.
Why not? Because if something has a dimension, say d plus 1 and then n,
Okay?
right? And if it's inverted, then it's n and d plus 1.
That's not called inversion. That's the transpose.
Okay, got it. Okay, thank you.
All right, let's resume. So far we have studied the linear regression problem. And the model looks like this. Linear regression is just simply y hat over there. Right? We wrote it in a matrix vector multiplication form. We want to find the optimal W to fit this model so that the y hat, the predicted value, is close to the true value y, the true label y. So we want to find the best W to minimize this E in like that. And we saw that there is a least square solution to it, and we derived the least square solution into a form that looks like this. Yeah, that's the least square solution. So, as alluded to earlier, there is a geometric interpretation of this, and let's take a quick look at it right now. So again, we have this linear model for prediction, right? If you look at this carefully, it's a matrix multiplying a vector, okay? So therefore, this product can be viewed as a linear combination of the columns of X, okay? It's a weighted sum of the columns of X. If you think about how this multiplication works. Okay, I know to quite a few of you, probably it's very hard for you to envision this, yeah, because you're not familiar with it, but I can help you on that, because that's something that comes from another course before this, yeah? Just to see that when you multiply a matrix by a column vector like that, you are actually adding the columns together and with a weight of W, okay? So if you're not comfortable with it yet, you have to read the textbook carefully and come back to the lecture and review this stuff, okay? We don't have time to discuss the details here, but note that linear algebra is very, very important in machine learning, okay? You will use it all the time, yeah? So make sure that you're comfortable with it. So this is linear combination of the columns of X. So basically, we're saying that what is the best linear combination that we can find, yeah? Being a linear combination of columns X, that means that y hat is in the space consisting of all possible linear combinations of the columns of X, right? That space that consists of all possible linear combinations of the columns of X is called the column span of X, okay? There's a fancy name for it, yeah? So y hat is a vector in the space called the column span of X. Okay? Again, the column span basically is the space where each point is a possible combination of the columns of X. Okay? It's an n-dimensional space because a column has is a length n vector. So you're looking for this point in the column span of X. And you hope that this point is as close to the original Y as possible. Yeah, the original true labels as possible. Okay? So we're going to view this Y hat as a point in space, and then Y as another point somewhere. Okay? So if we have the original, the known vector, which is the labels that you have in your training data. So this y is a vector that looks like this. And then let's use this two-dimensional plane here like this to represent the column space of X. Okay? In general, it's going to be n-dimensional space. Okay? So this is a MD space. This is the column span of X. Yeah? We know that y hat has to be in here. Yeah? Y hat is limited to this space because we know the y hat has to be of a form of a linear combination of the columns of X. Yeah? The question is, where should we pick this point, y hat? Yeah? This vector is y hat. This point here, of course, is the origin, O. Yeah? Yeah? So we're given the vector y. We want to find y hat, right? And we know the y hat is in the column span of X. It has to be in this space. Where should I put this y hat so that the distance between y and y hat is shortest? Right? Because we want to minimize that 2 norm squared, right? So our goal is to minimize y minus y hat squared. Whether you square or not doesn't matter, it's the same thing, right? To minimize it. Yeah. So this is the Euclidean space, Euclidean distance, I'm sorry. Distance between y and y hat. Okay. Right. We want to find a point that has the shortest distance to y. How should we pick that point? What do you think? Yeah. That's right. You make a projection. In other words, you want a perpendicular line to the space. Yeah? And that turns out to give you the shortest distance possible. So this line here should be a perpendicular line to the space. Okay? It's a projection. Yeah. To minimize this, the best y hat, yeah. In other words, the best y hat, we call it the y least square y, right? Yeah. Is the projection of the point y onto the space. That's the column span of X. And that means this line, this line, y minus y hat, has to be perpendicular to the entire space. Yeah. That also means that this line, y minus y hat, has to be perpendicular to any column of X. Yeah. So any vector in the space would have to be perpendicular to this line, right? So every column of X is a perpendicular orthogonal, yeah, fancier name, but they mean the same thing. Orthogonal to y minus y, which is the dotted line. Yeah? Orthogonal, well, the notation for two vectors being orthogonal, of course, is A orthogonal to B like that, right? It's the same as saying that. What is it? If A is orthogonal to B, how do we express that in algebra? Yeah, the dot product is 0, or the inner product is 0. Yeah, it's 0. Okay, so every single column of X has to have this relationship with this difference. Yeah. So therefore, that means if we take the inner product between this X, the columns of X, and then this difference, y ls, the one that we want to find, the least square solution has to be equal to 0. Yeah? Okay, the dot product has to be equal to 0 for every single column. And that means because our y hat is equal to x times WLS, right? This has to be equal to 0. Yeah. And if you write this thing out, LS is equal to, now we'll get back what we have before. This is y is a bar. Yeah? Yeah. And of course, this gives you WLS has to be, and that's exactly what we have before. Yeah. And this is the same as before, so it is expected. Yeah. We have managed to solve the same problem using a geometric analysis. Yeah, as earlier we used a pure algebraic analysis to find the same solution. Okay. Any questions so far? Are we doing okay? I know today is a bit challenging for quite a few of you. Yeah, so. But I hope we are still managing okay. Yes?
Why do you underline 0?
Oh, because it's a vector, right? Because it's a matrix multiplying vector. So it's a vector. Yeah. Okay. So one more topic about linear regression is the idea of regularization. Okay, it's an important idea for practical running of machine learning algorithms. There isn't a lot of theory there, but it's very useful in practice. Let's say regularized linear regression. And the solution would be, of course, the regularized least squares solution. Yeah. Previously, when we, in the plain version of linear regression, we try to minimize this. Yeah. XW is simply equal to the y hat vector, right? That's what we minimized before. Okay. And in the regularized version, we don't minimize this, but rather we add another term to it, lambda times w squared, like this, w 2 norm squared. Okay? And this is called a penalty function. Instead of directly minimizing the difference between the true label and the predicted label, we add a penalty. What are we penalizing? Anybody else? What are we penalizing? Yeah, because this weight, we want to add there, we want to minimize this whole thing, right? So we don't want this weight to be too big, basically. Yeah. So against large weights. Or the large 2 norm of W, if you will. Okay. The motivation for doing this is to avoid overfitting. Yeah, remember we discussed a little bit about overfitting. Yeah, that's the time when you train your model very well. Your E in is very small, but then turns out that when you use this model out in the real world, your E out, the testing error is pretty bad. Right? So the motivation is that we avoid this avoids overfitting. Sorry about that. Okay. So in other words, this when we have a large, let's say E out minus E in, the magnitude. Yeah, it's large. We don't want that to happen. And when does overfitting happen? Well, in the first lecture we mentioned that, well, if your data is noisy, maybe in that case you train your very good model to fit into the noise of the data rather than the real pattern of the data. Yeah, so you overtrain your system basically. Another possibility for overfitting is that you might not have enough data. In comparison with a target function that's complex. So this is compare with the complexity of the target function. So the idea of regularization is to just be a bit more cautious. Okay? You don't want to be too radical about your choices of W. Yeah? You don't want to have big values in some dimensions, for example. Okay? So, well, if we want to use the previous example about advertising, you have advertising on TV, on radio, or internet. Basically, you don't want to be totally and say, oh, okay, I think really you should put all of your money to advertising on TV. Okay, in that case, your W is very, very big. Right? You want to avoid that kind of solutions. Okay, even though that kind of solution might be very good for your E-in, for the particular few weeks of data that you have, may not be good for in general. Okay, that's the idea. You want to be a bit more conservative about your choices of W. So the target function in this example, not the advertising example, because I want to use this example from the textbook. It's one-dimensional example. The target function is sine of pi of x, okay, like that. And in the training set, the data points you have, turns out you only have 2 points. And let's say it's randomly chosen. Okay, so if pictorially we can draw it. This is x and f of x. This is the sine function, right? This is the true target function that you're looking for. Yeah, but you only have 2 sample points out of this. Let's say the 2 sample points are here. One here, and then the other one is here. Okay? Could happen, right? Just randomly you're given 2 sample points. And now you're asked to use linear regression to find the best fit to estimate this target function. Clearly, if you have more data points, you know this a lot better. Yeah? But we're considering a case you don't know whether you have enough points right now, right? So let's say you have 2 points only. Then what would be the best linear regression solution? If I do just use a line connecting these 2 dots, right? That line would be a perfect fit. In this case, actually, E in equals 0, right? You have a perfect training. You get this line, like that. Is this a good solution, though, in general? Yeah, but it's not, right? When you have other points in the real world, you will see immediately that this line is terrible. And this line turns out to be too ambitious, yeah, too radical, okay? And this is LS solution. Okay. What would a regularized linear regression solution look like for the same system? Yeah, like that. Same 2 points. Let's say here and there. Yeah, same 2 points. A regularized solution will be more careful, right? More cautious. I don't want to use very large W's, right? Because of that weight, that penalty there. When you solve this problem, you tend to get values of W that are smaller. Yeah? So you have a smaller slope, in other words. Okay? So likely you get something that looks like this. You have a smaller slope, depending on your choice of the lambda. Right? A line that looks like this. Okay? Supposed to be a straight line. Okay. Yeah. And you see, the line is not perfect, but at least much better than previous solution. Right? We get a feeling our big brain will tell us, our well-trained brain tells us that, well, probably this red line is a better representation of the previous red line, right? Better representation of the sine function. Now, it is, neither line is perfect, of course. Yeah, we're using a linear function to approximate a sine function. Clearly, we're not going to be perfect, right? But we can tell which one is better. Yeah. In general, this second red line will make less mistake than the upper one. Yeah. Okay. And that's the motivation behind regularization. Okay. So this is the RLS solution, regularized least square solution. Yeah, and the character here is that there's a smaller slope, right? Yeah. Okay. So, any questions so far about regularization? You're going to get a chance to play with this in your programming assignments. One thing to note is that in this form, this is a very general form, right? The lambda, if you set lambda to 0, then you go back to the regular linear regression. So this is without loss of generality, really, yeah? Lambda equals 0, then we go back to these squares. Then, of course, yes? Very good. Yeah. The question is, how do we find the best lambda? How do we choose lambda? Any suggestions? How do we sweep? When you sweep, how do you know it's good or not? Yeah. What do you mean by trial and error? So turns out that this is so-called a hyperparameter tuning problem in machine learning. And for those of you who know, this is one of the most challenging problems in machine learning. How do you choose these damn parameters? It always give you trouble because it's very hard to know for sure which one is good for this particular problem. The values you use for this problem will not be a good value for use to another problem. So every time you have to tune these parameters. Okay. And one way of tuning, a simple way to do tuning for our course is called validation. And that's something that we'll do later. Okay. So this is a topic for later. The short story is that during training, you want to predict how well this trained model will do in the real life, right? But you don't have any real life data out there. You don't have the historical data. Yeah. So the idea is that you take some of your training data out, use that data to simulate the testing data. Yeah. And then when you use that simulated testing data, now you can use that testing data to test how well this lambda work, yeah, how good it is, this particular choice of lambda. Yeah. And then you can try different lambda values and then keep testing using your validation data set. Okay. Yeah. So that's a short story, but we have a bit of more details to come towards the end of the semester. Okay, so now that we know that regularization usually is good, okay, so how do we solve this problem though? We have not talked about how to solve this problem, right? This is the problem. You want to have a penalty there. How do you solve it? Turns out that now then we have to minimize this guy, right? Like this. Yeah. Again, we take the gradient of this. Fortunately, we have well-known formulas for this. The first term, which is the same as before, right? 2 transpose. Okay, And then the second term, the derivative, basically, right? The gradient of the equation, the derivative of x, dx equals 2 times x, right? Yeah. So here you also have basically this is a square of the vector w. So again, you have the same thing, 2 times. I'm sorry, the 2 times that, so I have a 2 in front already. So therefore, lambda times the w like that. Okay. And again, we want this gradient to be equal to 0. Yeah. And this tells you that you want x transpose times x. And then I want to combine this w and that w together. Yeah. So I have a scalar lambda out. And then when I combine a scalar with a matrix, what do I need to do? I can't just add the scalar to a matrix like that. I have to add the scalar times the identity matrix. Okay. Be very careful about that. If you just add lambda, it would be a very different meaning. Yeah. This together, and then you have the w, right? And the remaining term x transpose times y, I'm going to put it on the right hand side, like that, right? Okay. And therefore, if you solve this, finally the regularized least square solution is x plus lambda I inverse x transpose y, like this. Okay. If you compare this regularized solution and the previous least square solution, the only difference is that you have this additional lambda I in here. Okay. If those of you who are really good at linear algebra, you will say that, okay, this one gives you more numerical stability when you take the inverse of the matrix. Okay. If you know, you know. If you don't, that's okay. Yeah. The reason that you add this lambda, you are increasing the smallest eigenvalue of that matrix, and that gives you numerical stability when you take the inverse. Okay. So that's another numerical benefit of doing regularization. But we don't have to worry about it in this course. Yeah. Okay, so we're done with linear regression for now. Okay, there are some other more advanced topics about linear regression that has to do with gradient descent, the famous gradient descent method. We're going to go there maybe next week. It's a lecture maybe. But for now, any questions about this? So far we looked at linear classification, linear regression. Then you ask, well, in the real world, our boundaries or functions are not always linear, just like that sine function, right? We saw the linear solution could be pretty bad, no matter what regularization you do. Okay, so how do we generalize? How do we extend this type of methods to work with nonlinear systems? Okay, there are at least 2 ways that we will cover in this course. The first way is to do a nonlinear transform. You transform your system from the nonlinear system to a linear system, and then use these linear methods. Okay? We'll talk about the second method later. But for now, let's say nonlinear transform. Nonlinear transformation. So again, the motivation is that linear functions may not be sufficient. One example is we might have a nonlinear classification problem. Yeah. Let's say two-dimensional problem. Yeah, just make it easy to draw. x1, x2, like that. And suppose we have a decision boundary that is a circle. Okay, unit circle, let's say. Yeah, 1 minus 1 minus 1. Yeah, and all of the pluses are inside. Yeah. And all of the minuses are outside. And this blue one is the true boundary that we don't know yet, right? We need to estimate the true decision boundary. And clearly, you can see that this is not a linearly separable problem, right? There's no way you can draw a linear line to separate the pluses and minuses exactly well, okay? On the other hand, we know that the circle will separate it very well. Yeah, circle will separate very well. So what do we do, right? What do we do? If we have some hints ahead of time that, yeah, a circle will separate well, then you can try to transform this space into a linear space. How do we do that? What is this boundary anyways? Can anyone tell me the algebraic expression for this circle? Yeah, x1 squared plus x2 squared equals to 1, right? That's what you learned in high school. Yeah, just like that. So if I want to convert this to a linear case, then I'm going to try define Z1 equals to x1 squared, Z2 equals to x2 squared, like that. Okay. If I do this, what will happen? Oops, I don't even have to put it here. I don't have much negative stuff. All the Z1, Z2, they are non-negative, right? Like that. This boundary becomes what? Z1 plus Z2 equals to 1, right? In the Z space. Yeah? So our boundary is actually now this line. 1, and oops, this is also 1, right? In the Z space. The points are also can be mapped from the X space to the Z space. Yeah? The mapping is such that the pluses goes where? Goes to under the blue line or above the blue line? Where do the pluses go? Below, right? Yeah, the pluses are smaller than 1, right? The x1 squared plus x2 squared smaller than 1. Yeah, so it's below. The pluses are all mapped here. And all of the minuses get mapped there in the Z space. And clearly in the Z space, the points are linearly separable, right? So then we can run our perception learning algorithm, for example, to find this line. Okay? So that's the idea of using a nonlinear transformation first, and then you apply your linear methods. So let's suppose that at the end, your PLA, you run it and linear separable, you run it in your Z space, and it gives you a solution that is exactly right. It gives you h of z is the sine z1 minus 1. Right? Suppose that's where, again, in general, your PLA will give you some random answer, right? That's correct. Yeah, it doesn't have to be this line. Then we know, since our mapping is known by us, yeah, the solution to the original problem in the X space, yeah, we can just map it back. So this is with sine of x1 squared plus x2 squared minus 1. Yeah, which pretty much, the circle, right? Again, yeah. Our big brain already knows it's a circle, yeah. But that's how you show the machine. So in general, we can always do this. Right? We're going to we design a new mapping from X space to the Z space by a mapping function called the phi, denoted by phi. Yeah? This is a nonlinear transform. Okay. So this is sometimes called a feature transform. Yeah, you transform, because x values are the features of the data points, right? You transform these features into a different form. Okay. And then suppose you are able to solve this problem using your linear separation. Either linear classification or regression doesn't matter. Yeah. The linear classifier. Let's say just use classification as an example. But notice that this is linear only in the Z space. Yeah, in the Z space. Yeah. Then g of x would be simply what? H of phi of z, right? Yeah. Because phi of, oh, I'm sorry, phi of x, of course. Phi of x is just z, yeah? Z equals phi of x. Now you can obtain this nonlinear classifier. In the x space. Right? We can always do that. Yeah? So even though we started with linear classifiers and linear regression methods, they could be quite useful as well. Yeah? Okay. As long as you know how to define this, how to design this phi. Everyone okay so far? So let's look at another example, which is a regression. So previous example is classification. Let's take a look at regression example. In particular, let's say it's a quadratic form of regression, so-called quadratic regression instead of linear regression. Yeah? To make things easy, again, we consider the case e equals to 1, yeah, one-dimensional space. Let's say we have a few points that you need to do linear fitting or quadratic fitting, actually, 1 and 2, and then let's say this point is 6 over here. Yeah, and this is y, of course. These are the 3 points, 3 data points that you're given. Yeah. So if you know that this is going to be a quadratic fit, then again, with our big brain, we already can recognize this pattern, right? That the perfect fit would look something like this, right? A quadratic fit, yeah? But how should we let the computer do it? How should we train the machine to do this? So in order to transform this space, this is nonlinear space, into a space where we can do linear regression. Okay? And knowing that we want quadratic in this X space. So the idea is to define this Z, this augmented vector, right? So Z0 is always equal to 1. Okay? I'm going to let Z1 equal to X. And then Z2 equals to X squared. Okay? So that's the trick. Okay? This is how I'm going to define the transform. First dimension of Z is X. Second dimension of Z is actually X squared. Okay, feel a bit strange. The same parameter, yeah, but makes a difference. Okay. So therefore now we know that d equals to 2, right, for the Z space. Yeah, in X space, d equals to 1, but in Z space, we get to a higher dimensional space. Okay. Almost always, you have to go to a higher dimensional space if you want to do more interesting things. Yeah. So, in this case, then we try to do linear regression, right? Y is equal to W transpose Z. Of course, now it's a W0 plus W1 Z1 plus W2 Z2. Yeah. But of course, we know that this is also the same as saying that this is W0 times plus W1 x plus W2 times x squared, right? Okay. So we do have a quadratic form in terms of x. But because we have a z space, it's linear, so we can use our least squares solution to find the w. Yeah? So let's just do this example, since we're new to linear regression anyways. Let's look at the different data points that we have. First point, let's say the first point is the one with label 6, yeah? y1 equal to 6, that one. Then what is the z1? It's that point, right? The point on top, yeah? The point on top, the x value is 0, right? So, but z0 is always equal to 1 because of the augmentation. So this x is 0 though. So x is 0, and the x squared, of course, is also 0. Yeah. Okay. So this is the first point in the z space. Everyone okay? Yeah. First point in z space. And the second point, let's say the point on at the bottom on the left-hand side. Yeah. So y2 equals to 0. But it's the left-hand side, so x is 1, right? So this one is 1, this one is 1, this is also 1. Yeah? X squared is also 1. Okay? So that's Z2. Everyone okay with this? Why Z2 is 1, 1, 1? Where do these ones come from? The first one is augmentation, right? Z0 is always 1. The second one is what? Because x is equal to 1. Yeah? Z1 is equal to x equal to 1. And the third one is because x is equal to 1 and 1 squared is also equal to 1. Yeah? Okay. Yes? Oh, we have to calculate the weight later. Let's first decide what kind of training data we have, right, in the Z space. And Z3 will be corresponding to the point, the right-hand side point, the x equal to 2. X equal to 2 and then y equal to 0 again. So y3 equals 0. And what is Z3? Well, augmentation, 1. This one is x, so it's 2, and then the third one is 2 squared, therefore it's 4. Okay? And altogether, therefore, to fit our least squares form, our big Z matrix will be 1, 0, 0, 1, 1, 1, 1, 2, 4, right? Like that. Our y vector is 0, 6, 0, 0. That's our y vector. Okay, these are the training data points we have. Yeah, 3 training data points. And the corresponding least square solution is, well, just substituting in that pseudo-inverse form, right? Let's put this matrix together, multiply things, da da da. In fact, because this is a square matrix, turns out that you can simply take the inverse instead of the pseudo-inverse. Turns out at the end, this gives you 6 minus 9 and 3 for your W, okay? Okay, like that. Everyone okay so far? Oh, after some messy calculation, the matrices and so on, you have to use a calculator or MATLAB or whatever. Yeah. You don't have to, but why waste time to? So that means what? Y is equal to 6 minus 9z, 1 plus 3 z2, right? That's our linear solution then. Yeah? The linear regression solution. Everyone okay? Yeah? And then how do we recover the solution in the X space then? Okay, how do you substitute? Yeah, yeah. Exactly. Okay, because we know the definition Z1 and Z2. x and x squared. You put this in, that's it. Then you're done. Right? If you try to plot this function, you will get exactly that one, the blue line. Okay, it's an exact fit because we only have 3 points, and we have a quadratic. We have also 3 degrees of freedom. There's a perfect match. Okay, so that's how you solve this problem by nonlinear transform. Okay, again, the idea is you have an original problem in the one-dimensional space, and you notice that it's not linear problem. Then you try to transform it to a high-dimensional space, in this case, 2-dimensional space, and it turns out that in that space you have a linear problem, and therefore you can use your linear solutions to solve that linear problem in a high-dimensional space. Then you map it back. You get this solution at the end. Okay? So that is the method of nonlinear transformation. Okay? So in a way, even though you only have linear methods, you can still handle nonlinear systems. So this linear solution that we have studied, linear classification and linear regression, they are quite powerful. Okay? They are more general than you might have thought. Okay. What could be a problem with this approach? Now we talk about the second approach. Yeah? This approach is fine. Yeah, it can work. What is the problem with it? Yeah. Exactly. Yeah. You have to know the transform more than the order. You have to know what kind of transform you should use ahead of time, right? To solve this, I know I want to make this assumption of this transform first. Fortunately, at the end, it works because this example I knew ahead of time, right? When you don't know ahead of time, what do you do? Okay, it's a challenging problem to find out what transform to use. Then you have to try different things. Yeah, try and error, maybe a bit validation as we try the regularization as well. Okay, so again, this is even more complicated than hyperparameter tuning because now you're tuning the functional form, which function to use, right? It's pretty challenging. Okay, but still, there are problems where you have some prior knowledge about your system, you have some expertise about the system, then you know, okay, this kind of transform will work or likely to work. You try those transforms, yeah? And if at the end the error is small, then you're fine, right? You get a small e in, then say, okay, I get the right transform. Okay? So still useful, but it would be nice to have a method that does not require us to know ahead of time what nonlinearity the system has. And that is the method of neural networks. So you don't have to know what is the order of polynomial, whatever, for that neural network. You just go ahead and train it. Yeah. So when we get there, we'll discuss this further. Okay, in 2 weeks, I think. Yeah. Okay. So we'll stop here and see you next week.